Welcome to this explainer. For much of the last decade, AI progress has felt, honestly, almost like magic. But behind the scenes, it's actually been surprisingly predictable. Today, we're diving deep into how the entire AI industry's understanding of machine intelligence has fundamentally shifted. We're not just looking at isolated, random breakthroughs here. We're going to trace a really fascinating evolution through three distinct eras of scaling, just to see what the future of AI actually looks like.
Here's our roadmap for the journey. We'll start with the decade of predictability, move into Era 1, where the goal was building a bigger brain, then Era 2, which was all about more food. After that, we'll hit the subscaling bottleneck, before finally arriving at Era 3, giving models time to think, which introduces a totally new scaling paradigm.
All right, Part 1, the decade of predictability.
So, for a long time, the progress of artificial intelligence was almost mathematically predictable. And this was all governed by what researchers call scaling laws. Think of it as a guaranteed recipe. If you simply add more compute power, the raw processing chips, larger model parameters, which are essentially the artificial synapses of the network, and more training data, you reliably get better capabilities. Period. It really felt like a fundamental law of physics for software. Just put more resources in, and you get more intelligence out.
Now, this foundational physics of AI development has literally driven the industry through three distinct evolutionary eras. And each of these eras completely redefined what it takes to build a smarter system. We're talking about a massive shift from sheer size to data volume to, ultimately, how the model actually thinks in real time.
Which brings us to Section 2, Era 1, a bigger brain.
Let's rewind a bit to 2020. We called this the Kaplan era. Based on the major scaling laws published back then, the industry adopted a pretty straightforward philosophy: just make the brain bigger. The Kaplan approach suggested that exponentially increasing a model's parameter count, along with the computing budget, of course, was absolutely the most reliable path to better performance. And this kicked off a wild industry-wide race. Everyone was pushing parameter counts into the hundreds of billions.
Moving right along to Section 3, Era 2, more food.
So making the brain bigger was great, but the industry soon realized these massive early models were actually incredibly inefficient. In 2022, DeepMind dropped the landmark paper on a model named Chinchilla, and it revealed that these existing giants were, severely undertrained. The big takeaway here? It all came down to a magic number, 20. Researchers proved that compute-optimal scaling required roughly 20 tokens, or pieces of training data, for every single model parameter. You couldn't just scale the brain anymore. You had to feed it a proportional amount of food.
That simple mathematical ratio fundamentally flipped the economics of AI on its head, shifting everyone's focus toward inference economics. Researchers figured out that smaller models, when deliberately overtrained on vast amounts of data, way beyond that 20-to-1 ratio, are significantly cheaper to run when you're serving billions of user requests. Actually, this is exactly why really powerful models like the Llama series are so affordable and accessible to us today. They prioritized a massive data diet up front to optimize for much cheaper long-term operation.
But then we hit a snag. Section 4, the subscaling bottleneck.
The strategy of simply repeating data or making models infinitely larger eventually crashed into a harsh physical and economic reality. As you scale up to 30 billion tokens and beyond, the loss curve, which is really just a way to measure how much the model's error rate is dropping, visibly bends. It pulls away from that predictable, straight line we saw in the earlier scaling laws. Researchers call this the subscaling bottleneck. The pace of improvement just drastically decelerates.
And why does this bottleneck happen? Well, mostly because of data redundancy. When you literally run out of fresh internet text and have to start cycling through the exact same data over and over again, the model just stops learning as effectively. It's a classic, brutal lesson in diminishing returns. Simply throwing more compute at the problem by repeating data? No way. That's no longer a guaranteed, cost-effective path to higher intelligence. Traditional pre-training had basically hit a massive wall.
Which leads us to Section 5, Era 3, time to think.
Now, it is absolutely crucial to understand that traditional scaling laws haven't failed, not at all. They just kind of found their limit in isolation. These diminishing returns forced researchers to uncover an entirely new dimension of scaling. Welcome to the test-time compute era. This whole paradigm shift is based on a really simple premise. If you want better answers on complex reasoning tasks, give the brain more time to think while it's answering. Instead of doing all the heavy lifting up front during pre-training, we are now scaling computation right at the exact moment you ask the question.
Right now, researchers are scaling this test-time compute through three main methods. First up, repeated sampling. That's generating multiple parallel answers and just picking the best one. Second is self-correction, where we actually allow the model to review its own work and fix its mistakes sequentially. And third, the most complex and honestly most powerful method, tree searching.
When you compare these search methods structurally, the difference is night and day. On one side, you have a standard, straight-line sequential search. But on the other, you have the incredible expansion of a Monte Carlo Tree Search. This advanced method allows models to actively explore completely different reasoning trajectories. Instead of just intuitively guessing the very next word, the model actually maps out various paths. It uses a verifier to check intermediate steps, which usually show up as green and red nodes, and it can even backtrack from dead ends. It behaves so much more like a human methodically working through a really tough math problem on a whiteboard.
Section 6. A new scaling paradigm.
This marks a profound, massive shift in the economics and the architecture of artificial intelligence. Inference compute is now a critical driver of capability. We're actively offsetting the diminishing returns of that subscaling phase we talked about by leaning into search algorithms. We are replacing those intuitive, immediate responses with deliberate, careful reasoning. Because of this, future AI progress is likely going to depend just as much on reasoning compute as it does on those massive, traditional training clusters.
So we are left to consider what happens next. Traditional scaling hasn't ended, but it's definitely gained a really powerful new partner. If larger models were the first era, and compute-optimal training the second, could deliberate reasoning at inference time be the foundation of our next great leap? Just imagine a world where AI systems are designed not merely to spit out a quick response in milliseconds, but to spend hours or maybe even days of meaningful computation, solving the hardest scientific and mathematical problems of our time. Now that is the frontier we are stepping into. Thanks so much for joining me for this explainer.